is mine, which is that Aaron already made this announcement, but there's an Arbeitsgemeinschaft happening over Wolfach Zimmer's conjecture, and applications are due at the end of this May. Again, I don't know if that deadline will extend, but that is the deadline currently. So.
Okay, so the speaker is David Fisher. We'll talk about arithmeticity, orbital.
So first, get rid of it. All right, I have orders. So first, it's a great pleasure to be here. I'm always happy to be in Israel and in Jerusalem, and this is a great conference. And it doesn't fall to me to do the job Alex just did and introduce the next speaker, because there isn't one, but it does fall to me to thank the organizers. And normally this is done at the end of the last talk, but I know myself, and if I leave it to the end of the last talk, I will forget. So let's thank the organizers now. All right. I can erase my other announcements too. I'm just going to start by telling you a theorem, which in the context of this conference, I think I can just state, and this is joint work with Uri Bader, myself, Nick Miller, and Matthew Stover. And what does the theorem say? Well, we've heard a lot about simple Lie groups, and today I'm going to like this particular simple Lie group, SON1, which is the isometry group of hyperbolic n space. And I'm going to have gamma in G a lattice, which will, again, at this conference, not surprise many people. And here's where maybe I veer off from where many of the talks begin. I'm going to pick a particular W, and my W, my subgroup of G, is going to be SON minus 1, 1, which is, you know, also the isometry group of some Hn minus 1 sitting inside of this Hn. And then I'm going to give you a very simple statement, which is if there are infinitely many closed W orbits, then gamma is arithmetic. And if you want to know what an arithmetic group is, if you were at Eve's talk yesterday, I guess that was, he gave you many examples, including two that were, his example 4 and 5 were in SON1. I feel obliged, which he didn't, to give you a definition, i.e. there exists a number field K such that gamma is sort of G of O of K, where here O of K is the integer points, and this tilde just means have a common finite index subgroup. And so I've just told you a theorem. I'll tell you another theorem that's part of the proof in the middle bit, but telling you a theorem, I should in some sense motivate the theorem. You can read this backwards, right? You can read this backwards and say, if gamma is not arithmetic, there are only finitely many closed orbits. That, in a conference where there's been a lot of talk about equidistribution, is probably the surprising conclusion, is that if gamma is not arithmetic, you can't equidistribute. I guess remark 0 is that in this context...
N is 3?
Ah, yes. N is at least 3. It's very funny. No matter what I talk about, N is at least 3, and I always forget to say it, even in different contexts. Yes. The other thing is about closed geodesics, and of course there are infinitely many. Most gamma, in some sense that can be made precise, are non-arithmetic. There are various versions of this. The best one that I know of is due to Galander and Levitt. I think he only has one T, but I forget. So So this, this tells you that for most lattices in SON1, we don't have equidistribution. The other thing I'll say about this is there's a translation, you can say this in terms of totally geodesic submanifolds. Of Hn mod gamma. And in that language, it answers a question asked by, well, I'll put them not in alphabetical order because I'll put them in chronological order. Asked first by Alan Reed and later by Kurt McMullen. The second thing I'll say about this, the translation here is sort of immediate, these things are stabilizers of submanifolds. Closed orbits correspond to closed totally geodesic submanifolds. If you like totally geodesic submanifolds, you can probably do the translation. If you don't like them, you probably wouldn't care if I did it. So I'm not going to do that translation today at any length. The second thing I should say is there's an observation of Reed from sometime in I think it's around 94, it appears in print, that says if gamma is arithmetic, and there exists one closed W orbit, there are infinitely many. And this really is an observation. It's not a theorem. And how do you prove the observation that's not a theorem is, you use the fact that the commensurator of gamma is dense and to push the closed orbit around. Maybe in a conference where we're talking about homogeneous dynamics, you could say take Hecke operators to push the closed orbit around. Maybe that's more familiar language to some people.
Are there arithmetic gamma that don't have a closed W orbit?
Yes. In dimension 3, yes. In dimension 4 and above, that is an open question. No, I'll say something more about that in a second. I don't really need codimension 1. We'll get to that in a minute. I want to justify this theorem before I say more technical things. Third comment that I feel obliged to make for, and third and fourth comment are about sort of history of the problem. Some special cases are due to myself with a slightly different team. Lafont, Miller, and Stover. And I just feel bad for Lafont that he got the special case but not the general case, so I feel like obliged to mention this. We got the case of non-arithmetic groups that were Gromov-Piateski-Shapiro constructions. And that's only about a year earlier, so this theorem, I think I should date it as definitely new theorem. And the last comment is in dimension 3, when n is 3, independently due to Margulis and Mohammadi. And I have to talk about this work now because I kind of, I have faith in these guys. And right now I get to say my theorem is in all dimensions and theirs is in dimension 3, but I kind of believe that, if I give this talk a year from now, I won't be able to do that anymore. And so, there are real reasons why they don't have it that I have discussed with them, but I have faith in them. So those are, just sort of comments about why this is an interesting question. And then I want to answer Heath's question about higher codimension, but again, I'm not going to quite answer it in exactly the same form for reasons that'll get technical. We'll call this one theorem A. And then I'll state over here theorem B, which is G and gamma as in A. Now I'm just going to let W equal SO L1, where L should be at least 2 and less than n, so any intermediate dimension. And there's a little bit of a problem to state something exactly in terms of orbit closures. It's an exact parallel of this, because when W gets small enough, W has centralizers, and then I can have infinite families of parallel orbits. Again, in a conference on homogeneous dynamics, many people know more about this than I do, but this is a technical problem that occurs all the time, so I won't say that. So what I'll say instead is assume there's a family of mu I that are W invariant. I'll state a theorem that's slightly stronger in some sense, W ergodic measures, that are properly supported, right? In this context, Marina's work is constantly in the background, so I am assuming that everyone immediately knows when I say I have a W invariant, W ergodic measure, mu I, that's properly supported. It's supported on a closed orbit of some intermediate group, right? It's not some random measure. It's some nice homogeneous measure, and we will use that certainly.
So properly supported is not a technical term.
It's not a technical term. So i.e.
some condition that you're not saying to us.
Well, support not equal to G mod gamma. This is actually a correct statement for what I need. It's a correct statement for what I need because of all these big machines, but it's a correct statement for what I need. And we just assume that these measures do equidistribute. So they should converge weak star to mu, which is R on G mod gamma. And then again, then gamma is arithmetic. And I'll say what's already been said in at least one talk, I don't remember whose right now, is that the fact that B implies A is essentially paper of Moses and Shaw, except this is such a special case of the paper of Moses and Shaw that one shouldn't really, their paper does much more than this, but certainly using the paper of Moses and Shaw, you can prove that theorem B implies theorem A.
You could also say that when you look at the normalize of W and then there are many.
Oh yeah, well, I can say things that I think of as more technical, and I'm not just.
That's much less technical than the condition you gave. Okay.
Yeah, no, I mean, there are many ways to phrase these theorems. There are many ways to phrase them in terms of measures, in terms of totally geodesic submanifolds, in terms of orbit closures. I'm just giving you two, and the reason why I went to this one is because this is what we prove, right? We prove this to prove that, to prove something about totally geodesic submanifolds. And even more, Amir and Margulis also, they prove this to prove that in the case they do a proof, And even more, they're, what's the idea for this? Which maybe is a little, maybe this is the first time this is showing up in this conference, although Yves did mention it briefly in his talk. The idea is that superrigidity implies arithmeticity. So one should give a superrigidity proof that's somehow adapted to this input. That's the idea. And now, okay, are there any questions on this? This is just the basic setup, the basic theorems, and I want to.
Superrigidity theorem you could state, which is somehow.
I will state the next thing I'm going to state is a superrigidity theorem. So I just want to be sure we're clear here, and then I will state a superrigidity theorem that we'll use to prove theorem B, and I'll even tell you what I will get through today is telling you why the superrigidity theorem looks related to theorem B. What I may not get through is telling you anything about how to prove it. So yeah, now we're going to prove that superrigidity implies arithmeticity, which is, an idea of Margulis's from the 70s. And, well, I guess for now I can slide this here. I don't think I managed my boards very well. So I just want to set up a superrigidity theorem. And the setup is a little technical, right? for those who don't know, I should perhaps refer to what Yves Benoit called yesterday Margulis's second arithmeticity theorem, was when he proved for the second time, and that time getting all of them, that higher rank lattices were arithmetic. He did this using a superrigidity theorem that was very general and had essentially no conditions on it. I'm going to give you a superrigidity theorem that has lots of conditions on it because there is no superrigidity theorem for these lattices that's general. So I need to give you a superrigidity theorem that's good enough to prove theorem B, but it can't be general, and so I now have to tell you some things about the setup under which I can prove a superrigidity theorem. So I'm going to start with rho from gamma to h, where h is an algebraic group over a local field K. K, is either going to be, real, complex, or p-adic, as it always is in these things. Luckily, we don't need positive characteristic, because I don't like it. And we're going to assume that rho of gamma is Zariski dense and unbounded. These, if you know anything about these business, are just sort of the assumptions everybody writes on the board next. Now I'm going to write down something else that's more than what people write down on the board next. I want to have a representation of h into GLV that's irreducible. And I noticed actually while preparing this talk, you need some extra assumption that is that the dimension of V should be at least 2. I don't want an irreducible one-dimensional representation because such things are stupid. At least 2, yes. Thank you. So I want to take some irreducible representation of V. You can notice, if you like, that I didn't bother to assume that H is semi-simple. The fact that I want an irreducible representation means that that's almost but not quite a lie. And I need V. And now, we get, I'm just going to think, I could give this a name, but then my notation gets too heavy. So I'm just going to think of gamma acting on V via this map rho. And, rho maps gamma into H, and then H acts on V, so gamma acts on V. And so gamma also, abusing notation, acts on the projective space of V. And I'm going to form an object that I like very much and have used many times, but that maybe isn't used as much by all the people in this room, which is we can look at a space called G times B of V mod gamma, and here there's going to be a left action of G. And this is just a standard induced action for people who know what it is, and for people who don't know what it is, I have to tell you how G and gamma act on the product in a way that commutes to tell you how to build this space. And so how do I do that? I want to act by G on G0 class of V, and then act on the right by gamma. If they're on the left and the right, they commute. And I do this, I do G, G0, gamma inverse, rho gamma, the class of rho gamma V. And that, I can then quotient by this gamma action, and I still have a G action on the other side. This is a standard construction that's very useful. And I should just mention that I can do that. Maybe my board use is I'm trying to rescue a disaster that can't be rescued. What? Yes, if you pass, certainly, I'm always assuming gamma is torsion free to make it a really nice space. This is this skew product space is a bundle over G mod gamma with fibroprojective space. And if you think about Uri Shapiro's lecture, we had a fiber bundle with the factors switched. But this this is the same kind of fiber bundle, but it's also nice, and this one shows up a lot. And what do I want to say now? I want to state for you theorem C, which is my superrigidity theorem. Same authors. Which says the following strange thing. So if there exists, and G and gamma are, G, gamma, and W are all fixed as at the beginning throughout the talk. If there exists a W invariant measure on this funny space, that projects to har, call this projection, let's give the gamma invariant measure a name, mu on G mod gamma. So, pi star nu equals mu in the notation I've set up. Then, if I have everything, rho extends to some rho tilde from G to H. So this is a superrigidity theorem. It's a superrigidity theorem that's slightly awkward to state, but as I said, there is no actual superrigidity theorem that's, Margulis's superrigidity theorem gets stated in the same way, but starting from here, he doesn't say any of this, and he just says gamma has higher rank. Here I, have to say all these extra things because I don't have an unconditional superrigidity theorem. Pi is the projection to G mod gamma, and mu is har measure on G mod gamma. Pi is this projection. I wrote it in words. I want a measure on here that projects to har measure on there.
What if I just...
It's a little tricky. And let me make some comments that explain why it's tricky. And I guess I'll make them on this board because it'll be easier for people to follow, I think. Yes, if W is amenable, and in fact that is the first, there's one way of viewing the first step of Margulis's proof of superrigidity, is he builds the same G action on the same bundle, but he uses P instead of my W, and for P, because P is amenable, P is the parabolic, minimal parabolic, since P is amenable, there's always some invariant measure that projects to har. This is one way of writing the first step of Margulis's proof. But if we start there, we get in trouble. Because that would prove his theorem that doesn't depend on my assumptions. So, some remarks. One is, in these hypotheses, there does not exist a gamma invariant measure on P of V. And it's relatively easy to see that that means there does not exist a G invariant measure on the induced space. So, there's really no G invariant measure, so because W is not amenable, so I don't get a measure for free, and because there's no G invariant measure, I have to be giving you something to get a W invariant measure. And I want to, this is the pedagogical thing that I'll say because I got confused by it when I first started thinking about this problem this way, which is the second remark is, so assume that we have rho from G to H. Then I should be able to give you, it's such that, that it restricts to my rho on gamma. If I can't tell you why there's an invariant measure under the conclusion, then clearly I'm telling you nonsense. So I want to tell you why under the conclusion you can build such an object with an invariant measure. And the point is, there's a trick that is also as old as the hills. So you have this G action on this space. There also is in this once G extends to H, there's also a G action on G mod gamma times P of V, which is just diagonal. Here you might be able to build a measure. When you have just the diagonal action, you might be able to build a W invariant measure. And the fact is, these actions are conjugate by the map that takes the equivalence class of G, equivalence class of V, to G, rho G of V. This is a two-line computation that this conjugates these two actions. And then, you know, if there exists a W invariant subspace let's call it V prime in V, or let's even say something better. If there's a W invariant line, which you might be able to arrange, V, you know, let's even call it L in V, then, well, L in P of V, that's the same thing as having a map from G mod gamma to P of V, and we can just take sigma and push mu forward along it. And then we get an invariant measure here. So if there's a W invariant line, this becomes a W invariant measure. And this construction of W invariant measures will come back later. It's how we build invariant measures, is we push things up from the base of the bundle to the bundle by finding invariant sections of the bundle. And if the representation already extends, then, you know, as long as the representation has an invariant line, we're good. And something I'll say now and say again later is if you have a representation with an invariant subspace, take some alternating power. I just gave you a representation with an invariant line. That trick also is as old as the hills. So the other remark I'll make is that, yes, I still have the theorem on the board, that's good, is that sort of once you have the theorem and you understand this point 2 well enough, this essentially classifies W invariant measures on spaces built this way. So I actually also have a measure classification theorem in a funny context of spaces. We never write it down explicitly in the paper because it's not, you know, the application is what's interesting in this context, but it sort of indicates that there's some other context that's slightly different than the ones we've looked at before, where there should be measure rigidity theorems. And I found it very interesting in Ari Shapiro's talk that he was also interested in such things, but with the bundle rearranged the other way around. You know, some hint that there's some direction missing in this subject of where else one might want to study invariant measures. All right, so now what I promised was to tell you why this superrigidity theorem has anything to do with arithmeticity, for which I have to do a few things. And okay, what's the setup here? So I have my gamma. It's sitting in G, and the first non-trivial claim that again is prehistoric is it lands in G of L, where L is a number field. And prehistoric means this fact is due in various pieces to Selberg, Calabi, Garland, and Raghunathan, all in the 60s. And you know, if you really want the bibliography, I can give it to you. It's also in the paper. And you know, this is for the case where G is SON1, right? That's the only case I'm talking about today. And so in that case, we have this that we've known since sometime in the 60s in various, you know, due to various people in various pieces. And I'm going to assume for this discussion that we're in the special case where I first stated things, because I think that case is interesting enough and it avoids some technicalities. There are technicalities that he wanted me to explain to you, and I'm not going to explain them. They're small technicalities. It's not incredibly hard, and I'm pretty sure they were well understood before I thought about this question. So in this context, closed W orbits What do they correspond to? They correspond to conjugates, or rather, you know, closed W orbits, or UI, my W ergodic W invariant measures, right? I'm assuming we all know those are the same thing because, you know, many people in this room have known they were the same thing since well before I did. And everyone else has spent the week learning it. These correspond to conjugates WI of W such that WI intersect gamma, which is gamma I, is a lattice in WI. And in particular, this means, you know, if you think about what this means in terms of the algebra of algebraic groups, WI is also WI of the same field L, and gamma is really sitting in these L points. In the what? No, I'm just using this fact. We're just using that there is a number field. This is something that, like, I was very slow to learn in my life, which I didn't realize, but there's this book by Alan Reed called the Arithmetic of Hyperbolic Three Manifolds. The fact that you're already in the number field for many questions about hyperbolic manifolds is step zero. It's, and this, this is.
If you have a non-arithmetic lattice, obviously you can't get somehow closed orbits with infinite volume.
I mean, we know by a result of, I guess Nimish is gone now. We know by a result of Nimish's that every orbit is either closed or dense. And so every orbit is either going to be closed or infinite volume. I don't care about the infinite volume ones today. I mean, the infinite volume ones can be interesting, but for today's purposes, they're not relevant. Yeah, every closed one will have finite volume. Every non-closed one will be dense. So we're just looking at the finite volume closed ones. You probably could do that, but it doesn't enter the proof because I'm assuming that we have the closed orbits that are closed, right? Those you can get some orbits that are W modded, Zariski dense, non-lattice probably, but Nimish has already proved for us in the 90s that those are dense, so they're not closed. All right, so what am I going to do with this data? What I'm going to do with the proof of, this is really Margulis's proof of arithmeticity. So I have rho from gamma. I could just take rho from gamma into the L points of my algebraic group, but what I want to do is twist that somehow. And sigma here is going to either be Galois conjugation, or, take L and localize at P, localize at a prime. And, for those of you who like the fancy language, what I'm doing is, there's one place of L that defines the embedding of L into the real points that gives me my original SON1. There are then some other embeddings of L in other fields that give me, other structures on G. And the point is, arithmeticity, and this is a fact that, as far as I know, was originally observed by Margulis, is equivalent to all of these rho gammas, all rho like this, having compact image. So what we're really doing is we're assuming that there's one that, we're assuming we're not arithmetic, so we're assuming there's one that doesn't have compact image, so i.e. assume run rho has non-compact image. And it's going to be Zariski dense just by construction in this particular G. And the one thing you should be aware of, because it enters into technical difficulties in our proof and even worse technical difficulties in the proof of Margulis and Mohammadi, is this G, you'd sort of like it to stay SON1, and it doesn't. It changes. It's, has the same, if it's a real group, it has the same complexification as SON1, but it, it might be SOPQ. It might be SOM plus 1C. These things introduce difficulties in the proofs. Darn it. Second time I talked about this work, so I missed an assumption in my superrigidity theorem, which I now have erased. I'm just going to write it here. For superrigidity, and I'm now reminded of it because it's about to come up, we need some condition that I was never planning to define for you anyway, so all I did was not write a mysterious word that I will never define if I succeed in giving my talk the way I want to. We need H is compatible, and all I really need for the talk is that the following groups are compatible. SOPQ, where P plus Q is 1, is M plus 1. SOM plus 1C, and all p-adic groups are compatible. And why do I list these particular groups? Because those are the groups that can come up when I do this operation. Those are the only groups, only H's I actually care about when I want to prove an arithmeticity theorem for lattices in SON1. And so that's what we're doing. And now we have this rho from gamma, and the fact is just that if I restrict rho to gamma I, or if I look at rho of gamma I, for these gamma i's, these land in, well, I just take Wi of the same L and I twist it by the same sigma. And you really should, pick one. Don't think about both. If you like Galois conjugation, think Galois conjugation. If you like p-adics, think p-adic. I'm trying to leave the option open so everyone can pick their favorite. It lands in this subgroup, right? And this is a proper subgroup of G of L sigma. And what am I going to do to build my invariant measure? I'm going to let H be the Lie algebra of, we're going to call this H to make it back in the setting of the superrigidity theorem. I'm just going to relabel G over this other field as H. Really, I've moved the global field and I'm completing to be over a local field, and I'm trying to brush all of that under the rug for anyone who doesn't like thinking about it. The Lie algebra of H is sitting here, and the fact is, if I let, let's say, K be the dimension of Wi, of W, which is equal to the dimension of Wi, which you can just trust me doesn't change under processes like this, then when I look at lambda to the K of H, and I call this V, is a representation where each Wi preserves a line. Namely, I just take lambda K of, oh God, now I've got myself really in trouble. I don't know how to write a Gothic W. Lie algebra of W sub I. It preserves the line that that's the alternating power of its own Lie algebra. And now I just do the same trick that I have written over here. So maybe I'll preserve this board because I'm about to copy it. Now, and I'm erasing the wrong thing, but now what I want to do, what this lets me do is that over each closed W orbit, which is just Wi mod gamma I, there exists a section sigma I from G mod gamma. It's a section of this bundle, which I guess I wrote sloppily before. It's a section of the bundle, so it's mapped from the base to the total space, and I just take Ui to be har on wi mod gamma I, and I push by sigma I forward mu I, and I call that nu I. And it gives me a measure on the bundle that's invariant under W. So this is a W invariant and even W ergodic measure, for all we care, on G cross P of V mod gamma. And now what do? I do, I do the only thing anyone in their right mind would do at this point, is I take nu I and I take some weak star limit point nu, and just, because this projects to mu I, and this, I said weak star converges to mu, I get that pi star nu is mu, which I promised you I was going to get. So this is how you prove arithmeticity from our superrigidity theorem. This builds you the measure that the superrigidity theorem calls for to be able to prove superrigidity from arithmeticity, to prove arithmeticity from superrigidity. And now I want to use the remaining time, of which I still have some, I'm happy about that, to tell you a little bit about how we prove superrigidity. And even though they're not here, I'll say it this way anyway. One of the things I want to do in telling you a little bit about how we prove superrigidity is advertise some recent work Botter and Furman have done rethinking how you prove superrigidity from a different perspective, because it turned out to be very useful in this context. I want to advertise their point of view. So the first thing I'll say is something I'll say nothing about the details of, because there are about 6 different ways to do it, and we could use about 2 of them in our context, maybe 3. Having nu gives a measurable map from G mod W to this H mod sum L. This is, let's just call this map something, we'll call it phi, where here phi is gamma equivariant, and L in H is a proper algebraic subgroup. There are about 6 different ways that one can, in various settings, go from having a measure on a bundle like the one I've described to having this one. Margulis did one in his original proof, essentially. Well, that's not quite true. When he gave the original proof, he used Oscillator's theorem, so he didn't do this. But when Furstenberg gave his version of the proof, or Margulis gave his second version of the proof, or Zimmer gave his version of the proof, they all did this. And the way this is now written in the paper, we use a neat new paper of Botter and Galander that apparently they haven't advertised as much as they should, so I'll advertise that too. But there are lots of ways to do this. And, the remark is that, if you go back to Margulis' original proof, you're really starting with a map from G mod P to H mod L at this point. Well, that's not Margulis' original proof, but one of these later editions of Margulis' proof. This occurs in Margulis' proof. And the difference here is really this difference that that group is amenable and this group is not. And it's a difference also between the structure of these groups. And the next remark is that Margulis uses that higher rank gives lots of centralizers. We replace that by using normalizers.
So centralizers of elements of gamma.
Centralizers of elements of, thank you. Right.
And normalizers of what?
Of elements of G also. So I'll be much more explicit about what we use. I don't want to be much more explicit about what he uses. Again, of elements of G. Let me just tell you what we use, because I'm being my attempt at vague motivation is clearly failing. So let me tell you what we explicitly use, and it will make clearer what I want. It's true. Normalizer of a single element is not very well defined. I use normalizers of subgroups. there's some obstruction to making this shift in his thinking from centralizers to normalizers, because elements have centralizers, and the relation of centralizing is symmetric, and this causes it to be less transparent to see than one would like that you can switch to normalizers. It really is somehow, he should have seen this, but he shouldn't have seen this because he had no use for it. But, you know, had he had a use for it, he might have seen it in the 70s. So I just want to tell you about some subgroups in SON1 that will appear in our proof, because it tells you something about why I care about normalizers, and then I'll tell you how we use them, provided I don't run out of time in the middle. So, you know, I'm going to take U, the Horo spherical subgroup. In SON1, I can take U prime to be U intersected with W. It's also the Horo spherical subgroup of W. And the fact is that if, you know, I take P in SON1 to be the parabolic, I have an interesting chain of normalizers where U prime is normal in U, is normal in P. And then I have one more weird fact, which is that if I take the diagonal A in SON1, well, A is a subgroup of P, but it's not normal. This causes conniptions for our proof because we want to work with A too. And the normalizer of A is bigger than A. It's the Weil group element times M times A. I don't really, if you don't know what these things are, I don't care. What I really care about is the following fact, is that the normalizer of A together with U generate G. So we're going to play some game using this exact subgroup structure. These are the subgroups of SON1 that show up in our proof, and these somehow replace in Margulis's proof the use of root subgroups and, you know, things that come from structure theory in maybe a more obvious way. You know, finding that these are the groups to use is a substantial part of what, from our point of view, one needed to do in order to prove a superrigidity theorem. To find that these are the groups you need to use and that you could use them is a substantial part of the difficulty. And I have to give you, yeah, okay. Hopefully it fits. Some things from Botter and Furman. The first of which is a definition that's a little bit complicated. It says, okay, I'm going to take T, I'm going to take G and gamma as above. You really can take G and gamma much more generally, but this is what we care about. You take T in G as subgroup, any subgroup. And I'm going to define, I'm going to take rho, you know, I'm going to have fixed, you know, gamma H, and even my rho from gamma to H above. It's just keep it fixed. I'm going to take some subgroup, some map from pi, you know, I'm going to take some subgroup L and H, and some map pi from T to the normalizer of L mod L. Which is a strange thing to take, but this defines a right T action on H mod L. Right, if T's in this normalizer acts on the right here. And we're going to call a map phi from G to H mod L. Maybe I should call this one psi from G to H mod L because it's not that one. Is a T algebraic representation if it's equivariant in the normal, in the obvious way, which is it. And this, it's an inconvenient tradition that we write this way. Some reason the sides on which things act switch between domain and range, and this is, you know, you can blame Margulis for this because he did it first. And I can't somehow, I could try and give the talk breaking that tradition, but then I'd mess up twice and you'd be confused. You're probably confused anyway. But So this is some kind of object. It's a complicated seeming object. It turns out to be a very useful object, and what I will tell you is that if you read Grisha's proof of superrigidity very carefully, you will find one such object in his proof. And this, Botter and Furman, I'm not saying something they wouldn't agree with. I wouldn't take advantage of their absence, and besides, I'm on videotape. And now I'm going to, now I'll say something on videotape that I shouldn't. I disagree with them very slightly about the way they present their work. They present their work in terms of category theory, and many of you have probably seen Uri preach the category theory, and the category theory they're using isn't very hard. And because we are who we are, I feel that many of you probably have heard this and thought, oh, category theory. So I want to say everything without referring to categories. You can translate it back to his way, or to my way, or to his way, or to my way very easily once you understand the words, but I'm going to do it without that. So I'm going to give the following definition, which would be occurring to Uri a bastardization of what's in their paper rather than what's in their paper, but all right. We're going to call an algebraic representation initial if there does not exist any L prime subgroup of L and algebraic representation phi prime from G to H mod L prime. So I just want to have fixed the smallest subgroup possible for which I can build such a widget. Now, the immediate question is, give you examples.
Let's say Margulis proof. So T is probably a torus, L is what is sort of an SL2. G is SS3, then T would be a torus, L would be SL2 times.
Oh, is that right? Let me think for a second. Yeah, T would really, in Margulis' proof, T would be a singular element. And then T would switch to being, in their proof of Margulis' theorem, T alternates between being a singular element and being unipotent centralized by the singular element. You sort of play games where you switch back and forth between those. And then what you really want to do, and I'll say this now and I'll say it again at the end of the talk if I get there, there's a magical observation they've made that is one of these magical observations that's very close to implicit in the literature, but that is definitely theirs, is that somehow getting L to be trivial is the game. If you can make L trivial for algebraic representations of some groups, then you're in really good shape to prove superrigidity. So the game is always forcing L to be trivial, and how the game is played is you relate algebraic representations for one group to algebraic representations for another. So the game is to make, in all the cases where theorems are proved, eventually the theorem is proved by proving that L is trivial. So let me see if I can say enough to allow us to sort of see why that might be true. So there's a theorem that I'll attribute to Botter and Furman, which again, Uri would say definitely is a bastardization of their theorem, which is that initial algebraic representations exist. That's just some Noetherian condition type argument. It's a little trickier than that, right? Because I have to carry the rest of the data. It's a Noetherian argument twisted by something. If phi naught from G to H mod L is initial for T, and phi from G to H mod L prime is another T algebraic representation, then there exists a map, F. Okay, this is the initial one, so it's going to go from H mod L to H mod L prime. And here, you know, we'll respect their wishes by drawing it as a commutative diagram. Because I actually think it's easiest to understand. It's a commutative diagram, and this is an H equivariant map.
But T is fixed?
Yes, T is fixed for now, and then I'll state one more thing, and I'll put it, you know, so really this theorem has three conclusions. One, this. Two, this. Three, the initial object for T and the normalizer of T are the same. And this is very interesting. I'd sort of discovered independently that you could do something with normalizers, and then understood that they discovered it before me. And it really is, if you read Grisha's proof again and you read it and try and translate it into this language, you'll want to write here a centralizer. And it's very important for us that you don't write a centralizer and you write a normalizer. So now I'm going to give you our cartoon of our proof. Using this subgroup structure and using that, so I won't keep this. Well, I guess I can just, no, that's written on too, so. This is the cartoon proof of superrigidity. To just tell you why that board and that board are actually related. So we can look at the initial object, the initial representation, initial object. I slipped back into their category theoretic language. I really am. I will say this. I'm convinced that the category theoretic language is nice. I'm just convinced also that it's scaring people away. And that's why I'm trying to avoid using it. We look at the initial object, and I've just told you that the initial object for U prime is the same as the initial object for U, which is the same as the initial object for P. And one thing to notice here is that U prime isn't normal in P. But I still get the initial objects to be the same all the way up the chain because this one's normal in this one, and that one's normal in that one. And the first observation is that since
So this initial is a representation of
this is a map from phi from G to H mod sum, let's call it L1 because I want to call L something else, together with a map that really is from all of P to the normalizer of L1 mod L1. So that this is P and gamma equivariant. That's what I have. And now since let's call this psi, because I was trying to do that. Since I have this map phi from G to H mod my original L, which has since been erased, right? This is what I got out of my measure. I got such a map. This map is W invariant, so U prime invariant, so is a U prime representation. So the fact that this thing exists tells me that L1 is not equal to H. Because there is some U prime representation where there's a subgroup that's proper. It says this guy over here is not all of H. I get some proper subgroup, right? If I just have, you know, I can have this map.
L1 equals H. That's what you meant.
Oh, thank you. Yes, so we get that. We get that those are not the same, so I have some non-trivial thing. And now this thing, I didn't tell you what its definition is. We've had long arguments about what we should actually name it, and my current joke is we call it compatibility because it is compatible with our proof. It has no better excuse for existing than the fact that it works in the proof. That's my absolute belief. Compatibility then implies that L1 is the trivial group. It's basically what the definition is rigged to say. And you can verify it for all the groups that matter for arithmeticity. And once you know this, then we really have phi from G to H. And I told you this means we win, and why does this mean we win in this case? Or not phi, this is psi. Psi here is a map from G to H, is also the initial object, or the initial representation for A, well, because it has to be, because you can't make anything smaller. And so for n of A, and this group here that's the normalizer of the trivial group mod, the trivial group is just H. And so at very least, what I've done just by this soft manipulation is I've built, you know, n of A times P generated group, which is all of G, a map from G to H. And I have to tell you why that map from G to H extends my original gamma representation, but that is really very much a recasting of very classical manipulations. So, you know, just this manipulation with normalizers proves the theorem once you have things set up right. And the other thing I will say, since I'm already over time, is to advertise further what Uri and Alex have done, is that, you know, a theorem I just erased, which I shouldn't have erased, because I'm doing that all day today, is what's the proof of that theorem? The proof of that theorem is just there are standard arguments in this area that also show up in some measure rigidity proofs, where you just say, oh, this action over here is ergodic, this action over here is tame or smooth. Basically, it means the orbit structure is a T0 space, and if I have a map between them, it's constant. You use arguments like that. If you were to write it sloppily the way I would write it, you would use them 5 times. They write it very elegantly, so they use them exactly once and then sort of reuse what they proved with them repeatedly. Very elegant paper. I recommend it. Thank you. For SUN1, we thought very briefly we had a proof, and currently we don't, and Uri and I got back a partial result yesterday afternoon. The problem, actually, it's very funny. If I look at what compatibility says, compatibility in that sense says if this H is SUN1, compatibility only implies that L1 is the center, Z is the center of the Heisenberg group. So the question is, do you want the definition of compatibility that works once n is 4, or the one that also works when n is 3? There's a difference. I'll give you the one that works as soon as n is 4, which really just is the following statement. Compatibility really is, suppose I have a map from P to n of L mod L, where L sitting in H is non-trivial, and just assume, call that pi, that pi restricted to U is not trivial, then L is trivial. Oh wait, you know, I said this wrong, but if I have L and H and this pi restrict to U is non-trivial, then L is the trivial group.
And L is their like initial object.
L is this thing, but this is true for any L. U is this parabolic, is the horospherical group, yes. As soon as the horospherical group is non-trivial, which you can verify, then the L has to be trivial. And it's a very odd fact that for these particular groups, for these particular choices of SOPQ and SOM plus 1C, this happens to be true, but it's not hard to verify.